Hello students, welcome to All Force e-learning channel. This is Nageshwar Rao, physics faculty, and today we are in session number 33. Yesterday you were informed about graphs related details and acceleration was introduced. I told you the reason why we have started with the graphs. Graphs discussion has connection with whatever we will be discussing further, so that graphs part was introduced to you. And coming to this velocity time graph, I have discussed only one point. What is that point? If velocity is constant, how does the graph appear? VT graph. It will be a straight line parallel to time axis. That's what I was told, and that's what you have seen yesterday, isn't it? So I'll continue with velocity time graph further. Like I'll talk about a few other points, few other physical significances connected with the velocity time graph. And regarding acceleration, what did I say? I said that acceleration can be categorized into four types. What? Average acceleration and instantaneous acceleration and uniform acceleration, non-uniform acceleration. Okay. Of course, acceleration's opposite is what? Retardation. Opposite in the sense, so basically acceleration in the sense increase in velocity. That's how we look at it. If velocity is decreasing with the time, in general, acceleration is change in velocity with time. If that change is increase, you call it as acceleration. If that change is decrease, you call it as retardation or deceleration, or you can also call it as a negative acceleration. Okay. So these are the four important things, and I'll deal with this one, uniform accelerated motion. Okay, corresponding to that, if I wanted to draw a graph, that is, this is how it can be drawn. Uniform acceleration. Uniform acceleration in the sense, velocity change is equal in equal intervals of time. If a body is, traveling along a straight line path from A to B, let us say, okay, these are time slots, let us assume like that, 1 second, 2 seconds, 3 seconds, 4 seconds. Okay, so here let us say it is having a velocity equal to 3 meter per second. Here it was having a velocity equal to 4 meter per second, 5 meter per second, 6 meter per second. So as it is traveling from A to B, what is happening in each second, there is an increase of 1 meter per second velocity. Okay, and it's uniform. It's not like, in 1 second there is an increase of 1 meter per second, in the other second there is an increase of 2 meter per second. If such a kind of change in velocity is there, you say that it's a non-uniform acceleration, isn't it? You say that the body is undergoing non-uniformly accelerated motion. Let us draw one graph corresponding to this one, corresponding to what? Uniform acceleration. I'll take time on the x-axis, seconds. I'll take velocity, which is measured in meter per second, on y-axis. Okay, so what I will get if I draw a plot, you can take these values itself directly, 3 1 4 2 5 3 6 4, like that. You will get a straight line, something like this. Okay, some one coordinate will be what? X coordinate, here it is 1, y coordinate is 3, 1 comma 3, 2 comma 4, 3 comma 5, 4 comma 6. You will get a straight line passing through the origin, provided initially at a time t is equal to 0, if the velocity is 0. What if a velocity is not 0 initially at when time t equal to 0? Then you will have a graph something like this. Okay, meter per second, y-axis, x-axis. So let us say it is having an initial velocity equal to u, and in this case initial velocity is 0. That's for the reason why the graph has started from the origin. If it is having some non-zero value of velocity initially, this is how the graph appears, connected with this uniformly accelerated motion. Okay, if there is uniform retardation, how it can be represented graphically? You can represent something like this. I'm talking about uniform retardation. This is how it appears. So here in this situation, but initially it was having a velocity equal to v, or you can take it as some u, no problem, u. So velocity meter per second, it is taken on the y-axis, time is taken on the x-axis. So finally what is happening to the velocity after some time? It is becoming 0. So there is a decrease of velocity with the time. As time is increasing, velocity is decreasing. This is how it appears if you are dealing with the uniform retardation motion. Okay. So let us get back to this first graph once again. We need to discuss certain key points connected with this first graph. I mean physical significances. I am trying to discuss with you whatever data is useful for for the next connected discussion. I will be discussing about deriving kinematic equations in case of uniformly accelerated motion using graphical method. So for that, whatever data is required, I am going with that. But at the end, I am going to give you a clear picture about all the graphs. Okay. Like if a velocity time graph is given, how corresponding position time graph can be predicted, such kind of details are there. I'll let you know all those things later. Even from this graph, you can talk about what average acceleration, instantaneous acceleration. I'm not discussing those things because they are similar to whatever earlier details I have given. Like in case of non-uniform motion, we have seen how average velocity, instantaneous velocity can be calculated from the graph. You have seen. Similarly, here also you can take a graph and you can find out a slope of a secant that gives us average acceleration, and the slope of a tangent can be calculated, and that gives us what instantaneous acceleration. And now let us find out the slope of this line, what it gives. Corresponding to this last coordinate, I'll take the value as v naught. I'll take the value as corresponding to this one, the x coordinate. I'll take it as t naught. Okay. So let us say it is making an angle theta. This line is making, this graph is making an angle theta with the x axis. So from here to here, what is the length? T naught. From here to here, what is the length? It's v naught. This is v naught, and this is t naught. Okay. Okay. Now tell me, what is the slope of this line? Slope of this line can be expressed as tan theta. We have seen in the last session, right? Tan theta. From this picture, what is tan theta? Opposite side by adjacent side. What is opposite side? V naught, and adjacent side is t naught. So velocity was divided with the time. When velocity is divided with the time, you can read this as the time, rate of change of velocity. You can read like that. If velocity is divided with the time, what it gives? It gives us acceleration. Isn't it? If velocity changes with the time, what it gives? It gives us acceleration. So in general, when you calculate slope from velocity time graph, what you are going to get? You are going to get acceleration. Remember this point. So this is nothing but acceleration. So the physical significance of slope of velocity time graph is what? It gives us information about acceleration. Okay. Slope of VT graph is equal to what? Acceleration. Now let us find out the area under the graph. Let us find out. If I calculate area under the graph, this is what is this? This is a triangle, right? Okay, half into base into height. That's what you are going to write. Okay, in this case, area can be written as half into base is what? T naught into height is V naught. Or in general, this is nothing but velocity into time. Velocity into time, isn't it? This is just a number. This is what? Product between velocity and time. What happens when you multiply velocity with the time? What you will get? You will get displacement. Velocity is equal to displacement by time. So velocity into time is what? Displacement. So this is nothing but displacement. So remember this point. If you calculate area under VT graph, what you are going to get? You are going to get displacement. These two physical significances are important. Further, I will be using these details to deal with further, other derivations. So what is the first significance? If you calculate slope of velocity time graph, you are going to get acceleration. If you calculate the area, you will get displacement. You will get displacement. So let us make use of these details to derive kinematic equations. So let us proceed with this. Kinematic equations are something which are familiar to most of you. S is equal to ut plus half at square, v is equal to u plus at, v square minus u square is equal to 2as, Sn is equal to u plus a into n minus half. Or kinematic equations in the sense in most of the books you will see these three equations. S is equal to ut plus half at square, v square minus u square is equal to 2as, and v is equal to u plus at. But there are two more additional equations. Those equations can also be treated as kinematic equations. Sn is equal to distance traveled in nth second. Sn is equal to u plus a into n minus half. And the other one is average velocity corresponding to a uniformly accelerated motion can be written as v plus u by 2. Simple mathematical average between initial and final velocities. So I'm going to derive all these equations using whatever physical significances were identified with the graphs. Using these physical significances, I'm going to derive all these kinematic equations. See, we can employ different techniques. We can describe the situation. We can go with the integration to derive kinematic equations. But for you guys, it's suggestible, for to go with this kind of method for NEET aspirants especially. Okay. Okay. See. Deriving kinematic equations let a body is moving with uniform acceleration. So here whatever equations I will be deriving, those equations are valid only when the body is undergoing uniformly accelerated motion, only when there is a equal change in velocity in equal intervals of time, whether it is retardation or increase in velocity, acceleration, whatever it is. There should be equal change in equal intervals of time. Then only whatever equations we will be deriving, those equations will be applicable. Because we haven't dealt with what the other possibility. What happens if acceleration changes with the time? We did not discuss anything about that. Usually we don't involve in the further discussion. Further discussion in the sense, see, distance, if it changes with the time, we called it as speed. Displacement, if it changes with the time, we called it as velocity. Velocity changes with the time, we called it as acceleration. Immediately, we get a thought, what happens if acceleration also changes with the time? It can be called as jerk, in fact. Jerk in the sense, there will be a sudden rise in velocity and sudden fall in velocity, or there will be sudden rise in velocity, like in 1 second 2 meter per second velocity rise is there, in the other second 4 meter per second velocity rise is there. In that case, if you are moving in a car or if you are in a giant wheel, okay, there will be jerk sometimes. So there will be what non-uniform variation in the acceleration. Acceleration also changes with the time. Okay, so that can be termed as jerky motion. Okay, we don't go into those details. Okay, so here we are dealing with a situation where body is undergoing uniformly accelerated motion. There is another situation where we can talk about a non-uniform acceleration motion. Non-uniform accelerated motion. Non-uniform accelerated motion in the sense what? There won't be equal changes in velocities in equal intervals of time. Such a kind of motion, if it is there, whatever equations we will be deriving, these equations are not to be used. You cannot make use of these equations to describe the situation. Okay, so whatever equations I will be deriving, children, remember these equations are valid only when you are dealing with uniformly accelerated motion. Okay, right. Let the acceleration be a. Okay, I'll define few other things. Let u is initial velocity, and v is final velocity after a time t. Okay, so this is the situation. I can put everything in the form of a graph. It was clearly mentioned in the description. The motion is uniformly accelerated motion. So I will have a graph something like this. Here initial velocity is not 0, it's u. So the graph is going to be a straight line, but it's not going to start from the origin because initial velocity is defined here. So you will have a graph something like this. Okay, I'll draw like this. We have 2 points. Time is taken on the x-axis. Okay, velocity meter per second on the y-axis. So initially at a time t is equal to 0, what is the velocity? U is the velocity. Okay, this is the origin. So this point is what? 0 comma u, 0 comma u. There is one more point. After a time t, what is the velocity? V. So let us say somewhere here you are having just to distinguish, I'll write it here as time. Let us say this is t. Corresponding to this, the point will be, let us assume that somewhere here it is. Okay. What is this? V comma t. And what is this? This is what? T comma v. And this is 0 comma u. So now we have 2 points connected with whatever description we have given. We have 2 points. If we join these 2 points, what do we get? We get a straight line. Okay. So just to show that I am joining 2 points here, I have represented like this. I will erase. So now I am going to join these 2 points. What I will get? I will get a straight line. Corresponding to this point, what is the velocity? V. Corresponding to this point, velocity is u. Corresponding to this point, what is the velocity? It's t. Okay. I will make some additional construction here, like this. Okay. Now tell me, what is the length of this part? From here to here it is v. From here to here it is u. So this part will be v minus u. If this is v minus u, this is also v minus. From here to here it is t. So this is how much? T. This is how you can take. There is a reason for considering these parameters, or for representing like this. Whatever physical significances we have identified earlier, those physical significances can be made use of here to find out acceleration, to find out displacement. We know that in case of velocity time graph, slope of velocity time graph gives us what? Acceleration, and area under velocity time graph gives us displacement. These were the 2 conclusions drawn earlier, right? So let us use the first physical significance. I am going to find out slope of this graph. Let us say it is making an angle theta. So therefore, slope is equal to what? Tan theta, and this can be written as opposite side by adjacent side. Opposite side is v minus u, adjacent side is t. And according to the whatever conclusion we have drawn earlier, physical significance of slope of vt graph is what? It's acceleration. Therefore, acceleration is equal to v minus u by t, isn't it? That is, a is equal to v minus u by t. I will take this as equation number 1. I will take it like that. Okay. So look at this equation. I am going to modify this a bit. This can be written as at is equal to v minus u, or v is equal to u plus at. Let us take it as equation number 2. This is one of the kinematic equation, isn't it? V is equal to u plus at. So when I have approached this situation with one of the physical significance of velocity time graph, what did I get? I have got one kinematic equation. Okay. V is equal to u plus at. So let us make use of another physical significance of Vt graph. What is that? Area under velocity time graph. If it is calculated, what do we get? We get displacement, right? So during this time t, when the velocity has changed from u to v finally, okay, we'll find out how much displacement the body has undergone. Total displacement of the body. Area under the graph is equal to, see, look at this, area under the graph in the sense that this is what you have to find out. This area, this entire area, you have to find out this area. Okay. So here this particular part has 2 different shapes. One is triangle, the other one is rectangle. So let us find out area of this triangle. Area of this triangle is how much? Half into base into height. Area of this rectangle is length into breadth. The length is how much? T. Breadth is how much? U. So this particular part area can be written as ut. So area is equal to ut plus area of this one is half into base. I will take base as time, this t. Height is what? V minus u. I hope all of you are able to follow this one. Base is t, height is v minus u. V minus u. And according to our previous conclusion, Now the area, what is the significance of area under velocity time graph? It gives us displacement. So I'll replace this area with what total displacement, S, total displacement. What is this? Displacement. Ut plus half. Look at this equation 1. From equation 1, v minus u, or from this equation, see here, v minus u can be replaced with at. So replace this v minus u with at. What you will get? At into t, at square. Let us take it as equation number 3. See, this is another kinematic equation. S is equal to ut plus half at square, isn't it? Let us proceed further. I'm going to make use of these two equations to derive further equations. Okay. See, in this equation, I can replace t with what? V minus u by a, isn't it? From equation 1, what is t? T is equal to v minus u by a. So replace here. S is equal to u into v minus u by a. I have replaced t with v minus u by t. Sorry, v minus u by a plus half into v minus u by a whole square into a, isn't it? So t is replaced with v minus u by a. So a gets cancelled. Okay, what you will get? U into v minus u by a plus v minus u whole square by 2a. Okay, and if you go with the LCM, what you will get? 2as is equal to, okay, here you will have 2u into v minus u plus v minus u whole square. You can take out v minus u common. If you take out v minus u common, what you will have? 2u plus one more v minus u is there. Okay, 2u plus v minus u. 2u minus u, it's u. So v minus u into v plus u. V minus u into v plus u is what? V square minus u square is what? 2as. So this is another kinematic equation. So we have derived the 3 kinematic equations. V is equal to u plus at, S is equal to ut plus half at square, and v square minus u square is equal to 2as. Here this S is what? Total displacement of the body in a time t. In a time t. Okay, so that's how you can derive the kinematic equations. Okay, now here we can think about another extra kinematic equations. Few other kinematic equations you can think about. I told you earlier, Sn, distance covered in nth second, or displacement of the body in nth second. Okay, even that is also considered as one of the kinematic equations only. There is one more kinematic equation. Average velocity associated with this uniformly accelerated motion can be expressed as v plus u by 2. Okay, we'll see how these 2 equations can be derived. Okay. So what are the kinematic equations we have derived? Let me write separately. V is equal to u plus at, S is equal to ut plus half at square, v square minus u square is equal to 2as. Okay, I'm going to derive 2 more equations. Let us consider displacement of the body in a time n seconds. In a time n seconds. I'll call it as S1. S1 is equal to u into how many seconds of time? T can be replaced with what? N seconds plus half into a into n square. So this is what? Total displacement of the body in n seconds of time. Okay, in n seconds of time. Therefore, I'll consider one more situation. Let us consider displacement of the body in a time n minus 1 seconds. What I'm trying to do is I'm trying to find out how much distance it has, how much displacement the body has undergone in nth second. distance or displacement, if it is traveling along a straight line, both are same. Okay, magnitudes will be same, isn't it? So here what I am trying to find out, see children, total distance covered in 5 seconds is different from distance covered in 5th second. Let us say in 5 seconds of time it has covered, body has covered 10 meters of distance. In 5th second, distance covered will be different. In 3rd second, distance covered will be different. In 4th second, distance covered will be different. So here, that's what I'm going to find out. I'm going to find out distance covered by the body in nth second. So for that, I have taken in n seconds how much distance it has traveled, and in n minus 1 seconds how much distance it has traveled. It's like in 5 seconds distance traveled by the body can be written, and in 4 seconds distance traveled by the body can be written, and just to take the difference, when you take the difference, what you will get? You will get distance covered by the body in 5th second, or displacement undergone by the body in 5th second. Okay, so let us find out. Let us consider displacement of the body in a time n minus 1 seconds. So I will represent this as S2. It can be written as u into n minus 1 plus half a n minus 1 whole square. Therefore, distance, or I am using this word, no displacement, so let me use the same word, displacement in the nth second. I will represent this as Sn. Sn is equal to what? S1 minus S2. Distance covered in or displacement of the body in n seconds, minus displacement of the body in n minus 1 seconds. S1 is what? Un plus half a n square, minus S2 is what? U of n minus 1 minus of plus, it becomes minus half a into n minus 1 whole square. So here you can expand this a little bit. So few terms gets cancelled. An square minus un minus into minus plus u minus half a into n square plus 1 minus 2n. So here un gets cancelled. Half a n square plus u minus half a n square minus of plus minus half a minus of minus plus 2 gets cancelled. You will have an. So half a n square gets cancelled, and finally we are left with u minus half a plus an. Here a is present in both the terms, so I will take it out. So u plus a of n minus half. So this is what displacement of the body in nth second, or distance covered by the body in nth second. Okay. So let us talk about another equation. So this equation Sn is equal to u plus a into n minus half can be taken as one of the kinematic equation. Okay. Now let us talk about average velocity. How do we write average velocity? Total displacement by time taken, isn't it? See, from this equation, total displacement S can be written as v square minus u square by 2a. Okay, and from this equation, how this t can be written? T can be written as v minus u by a. I will replace displacement with this equation, time with this equation. Let us see what we are going to get. VAVG is equal to total displacement v square minus u square by 2a divided by v minus u by a. So a goes to the numerator. You will have a here and v minus u in the denominator. A gets cancelled, and v square minus u square can be written as v minus u into v plus u. V minus u gets cancelled, and in the numerator you are left with v plus u divided by 2. So this is what average velocities expression is, and this too can be considered as one additional kinematic equation, and this is possible only when the body is undergoing uniformly accelerated motion. Okay, that's it, children. Okay, in the next class we will continue with a few numerical problems based on these kinematic equations, and later I will be dealing with the applications of kinematic equations, and then we will discuss the graphs part overall, overall graphs part. Okay, thank you, students.